Hi, today we're going to start into chapter 4, and in chapter 4 this is where we finally get into our hypothesis testing. So we'll be using inferential statistics, and remember that's the branch of statistics where we are trying to draw inferences to the broader population based on what we witness in our study. So in chapter 4 we're going to use inferential statistics to test hypotheses about the world. A hypothesis is a prediction to be tested in a research study, and that's usually something that comes out of your experiences, or and that could be your own personal experience in the world. It could be based on your experience as a researcher or as an expert in a topic area. It could come through your own research, or it might be part of a broader theory that's being studied. So a theory, by definition, is a set of principles that attempt to explain a psychological process. And often those theories lead to many different hypotheses. When we actually get into the process of hypothesis testing, we distinguish between two different hypotheses. We have a research hypothesis and what we call a null hypothesis. The research hypothesis, sometimes also called the alternative hypothesis, is the prediction about a difference that we expect to see or some sort of effect that we expect to see in our study. So if you think that groups will be different from one another, then your research hypothesis is that the mean of group A will be different than the mean of group B. Or if you think that you have a treatment or intervention that's going to lead to a decrease in symptoms, then your research hypothesis would state that you expect that the symptomology for population who gets the treatment will be significantly lower than the symptomology for the population who doesn't get the treatment. So notice that in the research hypothesis or the alternative hypothesis, we're always stating that we're making statements about a difference that we expect to see. The null hypothesis is the hypothesis about a lack of a difference or no effect. And every research hypothesis has a corresponding null hypothesis that's worded as the exact opposite of the research hypothesis. So it's the complement to the research hypothesis. And I'll give you some examples of that in a little bit. The reason that we set up our hypothesis testing this way is because what we're actually going to do is test the null hypothesis. So what we'll do is we'll consider the probability that the result of my study could have occurred, or the difference in groups that I witnessed in my study could have occurred if, in fact, the experimental procedure had no effect, or if, in fact, there's no effect in the real world. So how likely is it that I would have witnessed an effect by chance if in reality the treatment isn't working or the intervention isn't working? So in other words, if you're doing your study on some sort of intervention, maybe a new therapy, and you expect that the therapy is going to decrease depression scores, your research hypothesis is that people who get this treatment, this new therapy, will have lower depression scores than people who don't get the treatment. And your null hypothesis is that people who get the therapy will have the same depression scores or maybe even higher depression scores than people who don't get the therapy. Right? And if those scores really are lower for the treatment group, so you do your study and you see that people who undergo your new therapy treatment actually do have lower symptomology than the other group who didn't get the treatment, then something might be going on there, right? But we want to see, it could have just been by chance. So what we want to test is how unlikely is this difference to be just by chance? Because if it's very unlikely to have occurred by chance, then it probably is the case that your treatment had some sort of effect, that the therapy might have actually worked. Okay. So if the probability of your outcome in your study is very low under the null hypothesis, then we would conclude that the null hypothesis is rejected. So I reject that there's no effect, and as a result, or further, I support that the research hypothesis is true. So again, going back to the research and the null hypothesis, we're testing the null hypothesis. We determine whether we're able to reject the null hypothesis. And if we can reject the null hypothesis, we have support for the research hypothesis. Okay, so let's walk through another example because I know this is kind of an abstract, complex concept. Imagine that I know that my average exam score, without reading the textbook, I've been a terrible student this semester. I haven't been reading my textbook, but I've been able to manage an average exam score of an 83 with a standard deviation of 4. So in other words, we could imagine my distribution of test scores, average of 83. It may range to 1 standard deviation above 87, maybe even 91. Over here, 1 standard deviation below my average score, or 2 standard deviations below my average score, would be 75. Okay, so this is my distribution of expected exam scores, right? So this is where I would expect my exam scores to fall, roughly, around an average of 83. I may perform rarely higher than a 91 or rarely lower than a 75, right? But most of my exam scores would hover between 79 and 87. Okay, so then I read the textbook because I think I have a hypothesis that if I read the textbook, my exam score will go up. Or in other words, I have a hypothesis that reading the book improves test performance. So I do my experiment and I read the book and I got a 94 on my next exam. So I get a score that's way out here, 94. That's pretty extreme, right? Compared to my typical test performance when I wasn't reading the book. What are the possible explanations for me getting such a high exam score on this exam? Hopefully you're thinking that the possible explanations are either A, that reading the book really improves exam performance, that it works, right? Or alternatively, that reading the book makes no difference, but my exam score just improved. It just happened to, by chance, be a higher score than my average score, right? So if we look back here, I could have gotten a 94 on this distribution. It's not so unlikely, but it's pretty unlikely, right? So that's exactly what I want to assess, is how unlikely it is for me to have gotten such a high score, for me to have gotten a 94, knowing what my typical grades looked like. How unlikely is that 94 value to occur if the null hypothesis is true? Okay. And remember, the null hypothesis is the hypothesis that reading the book does not improve exam scores. So if reading the book does not improve exam scores, then wouldn't it be really unlikely for me to have gotten a 94 on this exam? I think so. So in that case, we would reject the null hypothesis, and we have evidence that reading the book probably does do me some good. So we'll keep talking about this core logic of hypothesis testing throughout the summer session, but for now, I'm going to move on into some more technical details of the process. So in hypothesis testing, we will be conducting either one-tailed or two-tailed tests. One-tailed tests are sometimes also called directional tests. And these are tests for which our hypothesis is set up in such a way that we are only interested in the effect in a single direction. So I'm only looking at one end of the comparison distribution. So if you look here, I'm only interested in a happiness score on the right side of this distribution, okay? And this would correspond, this visual here corresponds to an example hypothesis that could be, I think Mariana is happier or more happy than the average person. So if the average happiness score is 70, and I think Mariana is significantly happier, then I think she has a higher happiness score specifically, right? So I'm only going to look in the upper tail of this distribution. And because I'm only looking in the upper tail for a score that's specifically higher than average, we call this a one-tail or directional test. Alternatively, a two-tailed test, sometimes called a non-directional test, is a test in which we're looking for the effect in both tails. And that's because in a two-tailed test, we don't have a specific hypothesis about the direction of the effect. So for example, I might have a research hypothesis that states Mariana's happiness level is different than the average individual. So again, this is the average score, happiness score. I remember it being 70, right, from the previous slide. So if that's the average score, I think Mariana will have a different happiness score than the average individual. But notice that I'm not saying she's more happy or less happy. I don't have a specific prediction about the direction of the effect. I think she could be significantly happier, or maybe she's significantly less happy. Okay. And in that case, because I don't have an idea, a particular idea of which direction the effect will be in, I'm going to look in both tails. I'm going to see if she's significantly happier or significantly less happy. So I look for a significantly higher happiness score or a significantly lower happiness score. Okay, and this table is really useful. This table tells us what all the possible setups for our hypotheses could be corresponding to different one-tailed or two-tailed tests. So for example, if I have a research hypothesis that states that the mean of population 1 is different than or not equal to the mean of population 2, that's my research hypothesis, that the two populations have different means. Remember, my null hypothesis needs to be the exact complement of the research. So in that situation, the null hypothesis is that the mean of population 1 is the same or equal to the mean of population 2, that the groups have the same mean. In this case, because I'm testing whether the means are the same or different, right? There's no specific language about higher, lower, more, less. I'm not looking, you see no directional language in these here. I don't see any directional language. So in that case, I'm doing a two-tailed or non-directional test. Okay. So in this case, I'm just going to add a note, no directional language. Okay, so because there's no directional language in these hypotheses for the first row, I know I'm conducting a two-tailed test. If you do have a hypothesis that you think the mean of population 1 is greater than the mean of population 2, then we have a corresponding null hypothesis that the mean of population 1 is less than or equal to the mean of population 2. And in that case, because there is directional language, greater than, less than, we see that language occur, then we know we're doing a one-tailed test. Okay, and in this case, because I'm looking specifically for an effect that's greater than average, I'm going to be looking in the right tail. Okay. And then finally, in this third scenario, if I think that there might be an effect that's less than average, then I'll be looking in the left-hand tail, and that is also a one-tailed test. Alrighty, so in the logic of hypothesis testing, remember that what we're interested in is testing for how unlikely the outcome of your study is if the null hypothesis were true. So remember in the example of my exam score, right, 83 with a standard deviation of 4, right, then that corresponds to z-scores, a z-distribution, right? If we transform everything to z-distribution, we have a mean of 0 always for our standard normal z-distribution. And I can draw my standard deviations on here. Okay. So if this is my distribution that corresponds to a null hypothesis, I want to know how unlikely is that 94, that exam score of a 94 on this distribution with a mean of 83, right? So how unlikely? So I would, in this case, make a z-score so that I can stick it onto this distribution here. So my z-score is that 94. How unlikely is that to occur on a distribution with an average of 83, and remember a standard deviation of 4. That's from a previous slide. Okay. So what is the z-score for this test? You could calculate that z-score, and then you would put it on this distribution, right? And wherever that z-score falls in that distribution, we could figure out the likelihood of that value. So how likely or unlikely is a value of 94 on this distribution here? Okay, that's what this formula is telling me. How unlikely or likely is a value of 94 on a distribution with a mean equal to 83 and a standard deviation equal to 4? Or in other words, how likely or unlikely is a value of 94 if the null hypothesis is true, if reading the book really doesn't do anything at all? And in the logic of hypothesis testing, I will actually use cutoff values, or what we call cutoff values, to determine if it's unlikely enough for me to reject my null. Okay. So exactly how unlikely does a value have to be in order for me to draw a conclusion in support of my research hypothesis? Well, usually we say it has to be less than 5% likely or less than 1% likely. Okay. So with a significance level of 0.05, we're saying, okay, I'll reject my null as long as this outcome is less than 5% likely under the null. Okay. And in a two-tailed test, that would correspond to a z-score of that's more extreme than negative or positive 1.96. Okay. If you're doing a one-tailed test, you have to figure out which direction you're looking in. And if your z-score is more extreme than negative 1.64, if that's the tail you're working in, or positive 1.64, if you're working in your upper tail, then I conclude, okay, this score is less than 5% likely. I can reject my null hypothesis. Sometimes if we want to be more conservative, we will say, we decide as the researcher, I don't want to reject my null unless my outcome would have been less than 1% likely under the null hypothesis. And that's when I use these values here. So I could decide as the researcher, I want to be more conservative and only reject my null hypothesis if my result was so extreme that it was less than 1% likely to occur just by chance, by accident. Alrighty, and this is just a note of caution here. If you are using a one-tailed test and you witness a result in the opposite direction, then you cannot consider it a finding, right? So if I think Mariana is going to be significantly happier than the average individual, I'm looking only in this direction, right? Notice I'm only looking towards that tail of the distribution. But if Mariana's score is way down in that lower tail, I have to ignore it. I can't make a conclusion that she was significantly less happy because I wasn't testing that hypothesis. I was only looking in the upper tail for an effect. Okay. Alrighty, so in the next slides, we'll get into the 5 steps of hypothesis testing, and I'll do that in a separate video. Alrighty, email me if you have any questions. Remember that you can use the discussion board on Canvas also if you'd like to have discussion about this, or come to office hours on Wednesday. Good luck.